Once again, I'll begin by asking questions. In Daytona Beach, how is the quiz coming along?
I finally figured out how to access data.
Yay, Taylor! But should be just open. Yeah.
Okay.
That's good.
Me too, Taylor, don't worry.
Sounds like everyone's about the same place.
I'm almost done.
You're almost done. Jeremiah got it into me.
These things take a long time to run.
Whoa.
Depends on your computer.
Yeah, I've got a nice computer. It took me 30 to 40 minutes.
I wasn't able to access the WECA 3.7 page. I found a third party that has...
I know, I think it is.
Okay.
So I downloaded that. I just got the 3.7 from a classmate via flash drive, so I will be able to complete it now.
Okay. Anyone else?
One note is to show.
Everyone started it at least?
Yeah, I started it.
You started it?
It's
I mean, I've got a couple up.
midnight tonight? I'm not syncing.
Well, does anyone, who's going to need a little more time?
I should have it done.
You should have it done in Daytona Beach. Taylor? You just got access to it? You're going to need a little more time, or?
I should have it done by tonight, sir.
Okay. Anyone else? David?
I'm sending.
Okay. And is it, how does that pronounce? Lady?
Yeah. I'm going to later.
Okay. And who was the other one? Hemingway? Yeah.
Good. I'll send it. Yeah.
Okay, and here, Drew?
I'm done.
You're done. James, you'll get it done. Pablo?
I'm on it.
Now that you had a little bit of work on it. Yeah,
I have
James.
a question about it. The quiz dot says 10 iterations.
Yes.
We're supposed to run 10, right?
Right.
Okay.
Oh,
No, you changed it.
I changed it to 5.
Yeah.
That would be enough. Yeah.
Yeah, because we did the 10 in class and it didn't get through the run, remember?
I ran it on my, but mine has a solid state hard drive and 16 gigs of RAM, and it did it in like 2 minutes.
Like my desktop should rip through this easy, and it took me a half hour to do.
But it could be the hard drive because that's writing a lot. Maybe, I don't know.
I've got 2 SSDs and a 2T.
Yeah.
I've got lots of capacity.
Okay.
But it's
Okay.
taking me a long time.
That's good. What about? So I know that at least one person here had questions on the homework.
Yeah, I was doing that.
In particular, problem 22, and that was chapter 5 or 5, with a support vector machine. I don't know, back in Florida, have you started that homework?
No, sir.
Okay. Should we make it due Monday or Wednesday of next week? We have no class here in Colorado next Friday.
Oh, super. We have the same fall break.
Oh, we have the same fall break. That's perfect.
Kind of convenient.
Oh, that's a coincidence. It may be nice.
All colleges all break at once.
They should all have the same break. Okay, so
Devastating for spring break.
I figured that a lot of time and effort probably went into working on the quiz this week.
Yeah.
So we should postpone chapter 5 assignment.
Wednesday?
You want Wednesday before fall break or Monday?
I like Wednesday before fall break.
Wednesday?
Just before
So let's
fall
make
break.
assignment 5 due Wednesday. I can see some smiles there. I'll update the Google Calendar and the web page later then. So that the assignment 5 will be postponed until Tuesday, and but the quiz is due today, and I'll be grading this weekend, along with
So when's it due? Tonight by midnight?
tonight. So, midnight
For the quiz, you just want to
tonight. And I'll let you even use, James, what we did with one particular journal paper, or conference proceedings paper, the absolute latest midnight that you can find in the world.
I would be online looking for, yes.
Hint, it's in the it's in the Pacific Ocean.
Yeah, I forgot
It's
where it
beyond Hawaii. Okay.
Bangladesh.
Oh, so you have, oh, it doesn't quite match. We have class that Monday. We have Thursday and Friday off. They have Friday and Monday off.
is.
So,
That'd be nice.
Well, we could just skip class on Monday.
well,
On the 28th.
I'll be around for questions here.
Okay.
Okay.
Actually, that'd be nice.
So that works. Okay, with that in mind, I did want to go over problem 22 and get you started. I went through most of the details, and you can finish it up from there. So I think I got everything correct. So with that in mind, we'll begin the session, and then we'll go back to association rules. It's not, there we go. So this is problem 2 on the assignment, which is now due Wednesday.
22, right?
22, right, problem 22. So in this particular problem, we're going to be looking at support vector machines, and we're just going to walk through the process and use, I kind of gave when we went over support vector machines, I gave a broad overview of the ideas. There's a lot of conceptual underpinnings that we skipped over, a lot of linear algebra, optimization theory, quadratic programming. The prerequisites for the
I heard
course.
programming, that's all.
What?
All I heard was programming.
Quadratic programming, it's a particular part of optimization theory. It's not computer programming per se.
So that's why I'm so lost.
Well, if you take a look here at Adams, our finite math course, we go over linear programming, which is a particular problem involving, again, optimizing some particular, what's called an objective function, but you're constrained in the regions. You can't do it over all space, but you're really constrained to some, say, bounded region. It doesn't have to be bounded, it can still be an unbounded region in more general space. And there we're looking at linear constraints, and here you can look at quadratic constraints and objective functions. So getting back, and so I purposefully didn't cover all of the background material for support vector machines. The book goes through quite a bit in detail and goes through some of the steps to obtain some of the equations. And we're just going to look at using those equations to solve this problem. And it does use some ideas from multivariable calculus. So if you have had multivariable calculus, which I know not everyone here has, in the book they use, to come up with the equations, you take some partial derivatives, set them equal to 0 to find minimums and maximums. The other concept there from multidimensional calculus, if you've had it, is the concept of Lagrange multipliers. And that basically underlies that idea which we talked about of steepest descent, the gradient pointing in the direction of steepest descent. So, and that's related to the Lagrange multipliers and all of that. So, in this problem, we had 4 training points. We have, in 2 space, we have a point at x equals x1 is 1, x2 is 1, and that's classified as negative. And x1 is 1, x2 is 0 is classified as positive. 0, 1 is positive, and 0, 0 is classified as negative. So those are the points. And the first step is pretty straightforward, right? And it just asks you to transform each of those 4 points, your 4 inputs, using the transformation phi of x as 1 square root of 2 x1, square root of 2 x2, and so forth as given on the slide. Pretty straightforward. So we just do that. On the first one, x1 is 1, x2 is 1. So phi of x1 will be 1 square root of 2, square root of 2, square root of 2, 1, and 1. So that's phi of x1. And if you go through all those steps, there you see it. Phi of x1, exactly as we said. The other 3's had some zeros in it, and you notice the zeros showing up. Okay? Now, what is I should have stated, what is the problem asking? It's asking you to find the decision boundary. The boundary, the curve, or line, depending on the problem. And in this case, we're actually going to get a curve because we're in the nonlinear case here. And so we're looking at where the support vector machine will draw that decision boundary. So the first thing that we do is we transformed it into, in this case, we took R2 and now we're in R6. Right? And now, so equation 5.57, I didn't write down what that is. But basically, that is giving us the equation. Let's see here. I can write it as, where's the whiteboard? It's underneath. The problem with the smartboard is it always hides. So basically what that says,
do you have the equation?
it's basically the vector W is equal to, and so it's going to be the summation of your classifications times, so it's going to be your, so it's the sum of, and in Florida you'll see this in a few seconds here, lambda of I times your y of I being your classification, times your capital phi of your xi.
You should probably make that larger.
I should that.
Okay, can I make this? So I should make that larger. Let's see. Does it give me an option to do that?
Thanks. I think.
There we go. Can I select it and make it larger without doing it over? Or am I gonna have to type it over?
I don't know.
What about if I
Just
just,
highlight it.
yeah, probably select.
Yeah. I don't know.
The arrow off the top should be select.
Does that work?
Yeah.
Is that better? So we're gonna sum together, remember the lambda i's, those are those Lagrange multipliers that we're not talking about. There are some constants we're gonna try to solve for, but we're not solving it here. W is going to be a vector, and the idea is we're gonna multiply the lambda I with either a plus sign or a minus sign. So the y sub I is either a plus sign or a minus sign, depending on whether it's classified as negative or positive. And then times the vector phi of xi. Okay? Does that, maybe if I go to the next page, it'll be clearer. Because when we do that, so here is exactly what I just said. This is the equation. W is, in this case, the x1, the 0.11 was classified as negative. You see the negative sign in front, lambda 1, and this is phi of x1 from the prior page. And here I get a positive lambda 2 phi of x2 plus positive lambda 3 phi of x3 and minus lambda 4 phi of x4.
Where's the y of sub 1 come
Okay. The y sub I?
Yes.
in?
Okay. So, to make things abundantly clear, here's our test set. I mean, our training set.
That is it.
Here's y1 is negative.
Okay.
Y2 is that positive sign. So it went negative, positive, positive, negative.
Okay.
Right? And we see that on the next page.
That makes sense.
Or not on the next page. Here are the phis. And then I'm combining the lambda ones times the lambda times each of those 4 phis, but I'm putting the negative, positive, positive, negative into the expression.
Got it. I'm sorry.
Okay. So that's the first equation. And so our weights are going to depend on those values of lambda. Now, we've got, and I actually cheated a little bit. I didn't actually find the equation to give me that top equation, but I didn't look that hard. The sum of the weights is going to be 0. So that's the first equation there, or the sum of the Lagrange multipliers here. Now I've got these other equations, the 4 equations down here. And those came from equation 5.58. Basically, again, you're ending up with these signs, plus and minus signs in here. And multiplied by each other. So here, for example, the 9 is phi 1 dotted with phi 1. Okay? Forgetting the signs for the time being, the 4 is phi 1, so phi of x1. So let's back up. Here are the phi's again. So when I do phi of x1 dotted with phi of x1, dot product, we get 1 plus 2 plus 2, square root of 2 times square root of 2, plus 2 plus 1 plus 1. That comes out 9. When we do phi of x1 dotted with phi of x2, we get 1 plus 2 plus 0 plus 0 plus 1. So that's 4 for those who can do that. So you're starting to see where these numbers come from. Phi 1 dotted with x3 is 1 plus 2 plus 1 again, so you get another 4, and phi 1 dotted with x4 is 1. Then we're also going to get phi 2 dotted with itself.
Right.
Phi 2 dotted with phi of x2 dotted with phi of x1 is the same as what we had. Phi 2 dotted with x3, phi 2 dotted with x4, and so on.
So we'll have, for this example, we'll do that 4 different times then?
I mean, we get 4 equations.
Yeah.
Right? So here, should I write down 5.58? I maybe should have put that on the slide. Should I put it on the screen? It's pretty awful to write down.
Yeah.
Yeah.
It looks pretty crazy.
Right, it looks crazy.
Your explanation works a lot better than...
But so the lambda, so actually there's a quadratic term there, but really that lambda I, you're getting a sum 8, you're getting all this stuff equal to 0. So you don't want your lambda I out front to be 0.
Yeah, it's got to be...
So if you work through all of those,
That's for each thing.
notice the signs changing again, right? So when 1 is multiplied by itself, I get a negative times a negative. And then I'm getting a negative times a positive, a negative times a positive, a positive times, or a negative times a negative again. And then we get I had out front was that negative sign, so I'm getting a minus 4b minus 1 equals 0. And you go through these for each index, I going from 1 to 4. Does that hang in there? Kind of?
Yeah.
And so then here I'm getting, remember, phi 1 with phi 2 was 4. So phi 2 with phi 1, or phi of x2 with phi of x1 is 4. Phi of x2 with phi of x2 is also 4. And phi of 2 with phi of x3 is a 1. So you're getting all these values. And phi of x4 with phi of x4. Phi of x4, remember, was just 1, 0, 0, 0, 0, 0. So its dot product with itself is 1. So just finishing through all of those steps, you end up with this system of 5 equations and 5 unknowns. Lambda 1, 2, 3, 4, and b. And in this case, it's linear. We know how to solve it. We solve it. And here are the values that I obtained. More accurately, that Mathematica obtained.
Did you put in a matrix?
I just solved the system. So then, what are we going to do with those? Well, finally, I actually did include this equation. This is equation 5.59. It's the decision boundary. And what you have is the W, your weights, dotted with your transformed x's plus b. And that's what's inside this entire expression in the brackets. So W dot phi of x, at phi of x as, or phi of z if that's your test point, your new test point, plus b. And that's your linear separation. Okay? Remember how the support vector machine works, it uses these hyperplanes. So W is a 6-dimensional vector, phi as is phi of z. And I'm going to take W dotted with those phis, and my W's are this combination of my phi of x's that we obtained just prior to that.
So what's phi of z on this?
Z is your unknown point, Z is your unknown new point. Okay? So in our example, Z would be the pair Z1 comma Z2. You're going to transform that into your 6-dimensional space and then take the dot product with your weights. Okay. And then add the b, and wait, there's the b right down at the bottom there. There's your minus 1/4. And you're going to determine, given the values of Z1 and Z2, what's inside here will be positive or negative. That's the sign. Depending on what's inside here, I'm going to take the sign of what's inside here.
So
What's inside is your decision
why is
boundary.
x sub 2 in there twice and no x sub 4?
Because it's called the magic of copy and paste. As you're going through equation editor and don't want to type everything in again.
Okay, so that last x.
That last x2 here on the last line should be an x4.
Okay.
Yes.
Making it much simpler.
Does it make it a lot easier to understand how to go through the problem?
Yeah.
You should know typo when you see it, man. Come on.
Did you catch it?
Well,
Did I catch it? Did I look at it to catch it?
I figured it was a 4. I don't know.
So I thought that would be useful to see, so you actually can see that whole process kind of from start to finish in a problem that we can do by hand, or almost by hand, right? Okay. So, how was that in Daytona Beach? Any questions besides the typo at the very, very last line? Thanks for catching it.
You're welcome. I was just a little confused.
-1 for the day.
So, I turned on the microphone. Let's see if Daytona Beach has any questions.
Any question?
Pardon?
No, I have a comment
Yes?
about this. Yeah, the comment is, this is a heavy math for them. It's non-linear, it's vector space, but maybe graphically explain will be helpful. So look Murphy, you know, how look at the diagram here, the straight the circle and the straight line, and if you can somehow turn the line into a circle, and then you might see some kind of function of the field.
Right. So, I mean, I think, should I go back to, remember we did the support vector machines, we had that picture where we used the kernel function, the radial basis function.
Yeah, I remember that.
I can bring that up. Is that what you're asking, what I'm saying, Hong? I should maybe go back to that picture?
Yeah.
Okay.
Yeah, it describes this transformation effect to the points.
So I'll let me bring that back up. You don't remember? Okay.
So you remember that like 3D bell curve?
So let's. I'm going to bring it up here again momentarily. I'm loading it back in.
If we were able to use that to kind of separate things out, so when we drew a hyperplane through it.
I didn't go into the kernel
It's just stuff right here.
function. I tried to make this as simple as I could.
Yeah, that's
Support
what
vector machines in general are.
because that's what they did. They just did this thing, and if it were the third dimension, that's what it would be. It could be a dip or what the terms are.
Okay, here we are.
Yeah.
Or maybe this is.
But what are we talking about?
So the example that we did earlier is, here is an example of some data. And we have the blue dots and the red dots. And we want to figure out, if you recall, I can go back to support vector machines, but they generally are searching for hyperplanes. So it's the analog of lines in higher dimensions. So lines, planes, a three-dimensional straight structure in 4 dimensions or something like that, right? The basis for support vector machines is using these hyperplanes. And so the idea was, how do we handle data that's very obviously nonlinear? In fact, here it's pretty, almost too exactly circular compared to, in real life it might be a little more complicated than that. But here we've got more of a circular decision boundary that we're going to search for. Okay? And the trick is to what's it called? It's actually called the kernel trick. Okay? Is we change our inner product, our dot product, to a more complicated, we have kind of a function in the middle of our dot product. And so one example of that, which I can give explicitly, was called the radial basis function. And what we do is, or another way to think about it, is we transform, like we did in this example, these points in the plane to, say, points in 3 dimensions. Okay? Using some sort of function to take x1, x2 into some combination of x1, x2, and, or of first into 3 components. Some sort of function of x1, x2, another function of x1, x2, and another function of x1, x2. And so you end up with, say, this. Yeah, you had a question?
So, are there just a bunch of functions that people use for this, or are there times when you have to try and find the function?
Generally,
that's able to do this
there, I mean, that's a whole, I mean, that's an art form in itself.
Okay.
Okay? So, I mean, here, if you have circular, radially kind of like we had here, the obvious choice will be what's called the radial basis function, because what that does is it transforms circles into, in this case, of higher dimensional, it extends it as like a multivariate normal curve.
Sorry, I'm lost. I'm gone somewhere else right now.
Okay, so I basically, if you look, I probably used x1, x2, and then e to say the negative x1 times x2, something along those lines. So my z component is what I changed here, and probably looking at this curve, my x1 and x2 didn't change, but now I projected it into 3 dimensions using this new function. And this is what the curve looks like in 3 dimensions. And now, here's an example, that line that goes across is an example of a hyperplane, but now it's in not my 2 dimensions, but 3 dimensions. And so now notice the red dots are being cut from the blue up above. The red dots up above are being cut from the blue dots down below. So I am using that cutting. Does that, remember doing this?
Yeah.
When we went over support vector machines the first time?
Right.
So yeah, it's heavy duty mathematics, and a lot of this, that's why I didn't realize that I had given that problem on the homework until it was brought to my attention.
So what was Han saying about maybe using this instead?
Well, but this is what's going on. This is
okay, so
this is what you're doing by taking. Notice we took that x1 comma x2. That's a point in the plane, and instead I've now transformed it into 6-dimensional space. Right?
Yeah.
And now the points are separated in a different way in 6 dimensions. And it's in those 6 dimensions we're able to find that hyperplane. Similar to what we did here. The hyperplane separates it, and that's that weird function that ends up being this dot product at the end of the final slide that I gave.
Okay. So, from the point where we've got that final function,
Right?
we have to find the...
That's your what's inside those brackets, that's your decision boundary.
Okay.
Because if it's that positive, you say, I'm going to classify it as positive. If what's in between those brackets is negative, you classify it as negative. That's your hyperplane.
Okay, so this is
So
only,
that-
sorry, this is only for one hyperplane each time?
Well, yeah, that's all you do in support
Okay.
vector machines.
So is there gonna be something that we need multiple hyperplanes through set of data?
I mean, you could use it if you're trying to do things separated into more than 2 classes.
Right.
I mean, you could combine them to do that. So, for example, when we did it using Weka on this quiz, right? It's heavy duty math. I mean, Ryan Goldsworthy, Ben's brother, I don't know if
I've heard of them.
yeah, he did his senior project on facial recognition using support vector machines. And I pointed him to some resources, and the next week he came back and said, you know, those are all graduate level courses. So I don't expect you to know all the inner details of it, but more, how does it work and how do we get it to work in WACA? So what are the conceptual underpinnings? Okay, so did that make things a little clearer also in Daytona Beach?
Well, yeah, much better.
Much better? Yeah, I'm not going to,
This one,
I'm trying to keep the heavy math out of the situation as much as possible.
I don't consider that heavy math though, right?
Well, I'm trying to give you, I mean, what is the heavy math? The heavy math is turning this into a quadratic programming problem, and then solving the quadratic problem. Where do all these equations come from? That's pretty heavy-duty mathematics. Does that make sense?
All of this is just.
Okay. So with that, should we go back to association rules, or should we continue that maybe on Monday? Any preference here?
I'd rather continue that on Monday because
If we had to do this
we've only
all
got like
day.
6 minutes left. I don't think we can show it on Monday.
Monday, Drew, Daytona Beach also?
To each other one.
Should we just
yeah,